in the fifth lecture of week 1, which will be the last lecture of week 1, I will briefly review what we learnt in week 1 and then do a few practice questions. Okay. So, we have a review of week 1 and practice problems, which will be the content of week 1 lecture 5. So, first let us review what we learnt in week 1. In week 1 we learnt the general principles of solids, and we started with learning about the solid state of matter and different solid state materials. Then we learnt some very general principles of solid state thermodynamics, how enthalpy and entropy affect the formation of the solid state. We learnt about interaction between atoms or molecules, and we learnt about pair potentials very briefly, everything, and then we learnt briefly about phase diagrams, and we learnt the concept of different phases that can exist in a solid. Okay. And then we moved to the kinetics of crystallization, and again we saw this very quickly. We saw crystallization from melt, from vapor or from solution, and we learnt about nucleation, and we briefly saw what gives rise to different shapes of crystals. And then we, in the last lecture, that was lecture 4, we learnt about the general overall synthetic strategy, where you can either have solid state synthesis or you can have wet chemical synthesis. And let me emphasize that throughout this week we have just given very short overview of each of these things. We have not gone in depth in any of these. Okay. The idea is that you should be aware of these concepts, and we are, as I said, we did not discuss this in great detail, okay, but if you want, you can learn, for example, you can learn a lot about phase diagrams and issues of enthalpy and entropy from standard thermodynamics books. And we in this course I won't discuss too much about all these, okay, but at least I wanted to give you an overall idea. Similarly, we discussed very briefly solid state synthesis and wet chemical synthesis, but if you take any standard book on solid state chemistry, usually a whole chapter is dedicated to synthesis of solid state materials, and usually lot of different examples are given, okay, which showcase the different methods. And again, I have not tried to do that, I have not even attempted to do that, and rather I have left it to you to, I have given you the overall principles, and if you are interested or if you need to learn more of these things, you can learn them. Okay. So, now I will do a few practice questions. Okay. These are general questions that help you think about the concepts that you have learned, okay, and I'll just give a few, just 4 questions here. Okay. So, the first question is, are all materials more dense in their solid form than their liquid form? If not, give a counter example and use the phase diagram to explain your answer. Okay. So, the basic question is, if you take any material, okay, then is it more dense when it is in a solid than in a liquid? Okay. Is that always the case? That is usually the case, but is that always the case? If not, give a counter example. And I also said that you can use a you can use a phase diagram to explain your answer. Okay. And this will actually be related to the third question. Okay. The second question is, can a perfectly ideal gas be solidified? Okay. And what about a gas consisting of hard spheres? And then I said use the interaction potential to explain your answer. The third question is, what does the slope of the liquid solid coexistence line in the phase diagram say about the melting point? Okay. And derive an equation for the rate of change of melting point with pressure. When does the melting point increase with pressure? The next question and the last question in this set of practice problems is, this is actually a numerical question where we take solid benzene whose molecular weight is given and it is at 1 bar pressure. The enthalpy of fusion is given and its density of liquid benzene and solid benzene are given at the melting point, and you are asked to calculate the slope of the PT coexistence curve. So let us answer these questions. So the first question, are more materials are all materials more dense in their solid form than their liquid form? Okay. The answer is usually for most materials solids are denser than liquids at the same temperature and pressure. However, for water at 0 degrees centigrade and 1 bar pressure, ice is less dense than water, and you know that because ice floats on water. And a consequence of this is that the slope of the liquid solid coexistence line in the PT diagram is negative. Okay. So melting point decreases as you increase the pressure. Okay. And we will see this in the solution to question 3. So what I basically wanted to say is that if you look at the pressure versus temperature phase diagram, okay, for most materials you will see that it has it looks something like this. So this is a solid, this is a liquid, this is a gas. Okay. Now for this is for most materials. And what I mean is that this line has a positive slope. Okay. But for water, the phase diagram looks a little different. So it looks like this, and then this line actually goes like this. Eventually it comes back. Okay. So and goes like this. So the solid liquid, so the coexistence line of solid and liquid actually has a negative slope. So right here, right at the melting point, okay, the slope is negative. All right. Now the next question had to do with can a perfectly ideal gas be solidified? And the question is, what about a gas consisting of hard spheres, and use the interaction potential to explain your answer. So the answer is that if you take a perfectly ideal gas, it cannot be solidified since there are no interactions. Since there are no interactions, the particles, okay, it does not even make sense to talk about the size of particles, okay, but so you just think of particles as point particles, okay, and this is ideal gas. Okay, so the particles have no size since there are no interactions. They can go right through one another. One particle does not even see the other particles, and it is never possible to completely solidify it. Okay. Now suppose you take a gas full of hard spheres. Okay, so hard spheres are let me show them in this blue color. And I am emphasizing that to emphasize that they are hard, I am showing them as rounded balls. So if you had a gas of hard spheres, okay, now and let's say the size of each of the gas is the same, of all the particles are the same, and now what will happen is that this gas does not see the other particle. It keeps, so for example, if one particle is moving this way, it does not see this particle, okay, so long as it doesn't hit it, okay. But now if this hits this other particle, then it bounces off. So if it hits a particle, then it bounces off, okay, and so the particles actually, it is unlike particles which attract each other, okay. So it is unlike particles which attract each other when they are far apart, okay. These particles have no attractive forces, they only have the repulsive forces. So what we said, okay, if you remember the pair correlation function, we said that your V of R, the pair interaction function, not the correlation function. So the pair interaction function V of R is equal to 0 if R is greater than d, which is the hard sphere diameter, which is the diameter of these spheres, and V equal to infinity if R is less than equal to d. Okay, it's infinity means you cannot crush them, they are hard. Okay. And in this case, it turns out that if you pack them, and you can see this, I mean, you just take a bunch of balls and you push them closer and closer to each other, then you will find that eventually they arrange into an ordered pattern. Okay. So when it is sufficiently dense, okay, these will pack into a close packed pattern. Okay, I will just they'll closely pack into essentially an FCC crystal, a close packed crystal or an FCC crystal. So when the density of this hard sphere gas is very low, okay, then it will form an FCC crystal. Okay. What is interesting is that since there is no attractive interaction, since there are no attractions, okay, there is no difference between the liquid and the gas phase, okay, and we only have a hard sphere fluid. So there is so whether you call this a gas or a liquid, this phase, okay, you have a hard sphere crystal where everything is perfectly ordered, and then you have a hard sphere fluid where the particles are going around randomly. Okay, you don't have anything, you don't have a solid to a liquid to a gas, you just have a solid to a fluid in this case. Okay. And that is a consequence of the fact that there are no attractions. So, this V of r does not have any attractive term. Okay. So, the example of V of r with attractions. So, attractions, one example, okay, is the V Lennard-Jones, the Lennard-Jones of r. Okay. So, that has a over r to the 12 minus b over r to the 6. So, there is a term that is attractive. So, this second part leads to an attractive interaction. Okay. So, attractions are there in something like a Lennard-Jones, and again I want to emphasize that hard sphere, ideal gas and Lennard-Jones are all models. Okay. So, these are sort of idealized models of real atoms or molecules. So, an ideal gas, the particles do not interact at all, V of r is 0. For a hard sphere gas, V of r is only repulsive, it is either 0 or infinity, it is never negative. Okay, there is no attractive term. And for a Lennard-Jones potential, your V of r has both an attractive part and have both a repulsive part and an attractive part. Okay. So, next question, let us go to the next question. What does the slope of the liquid solid coexistence line in the phase diagram say about the melting point? And derive an equation for the rate of change of melting point with pressure. When does the melting point increase with pressure? Okay. So, let us quickly see this. Okay. So, the answer is that, and what we are really talking about here is this, if you look at this PT phase diagram and you look at any typical material. So, we are looking at this particular line. This is the liquid solid coexistence line. So, what it means is that along this line, if you are at this pressure and temperature, if you are at a pressure and temperature that falls on this line, then the liquid and the solid phase will coexist. Okay. Now, the question is, what is the slope of the coexistence line? So, what we are asking is, what is dP by dt along this line? Okay. So, what is dP by dt along this line? Okay. So, along this line has a certain slope, and what is that slope? Okay. And what this tells us is, this actually tells us how the melting point changes with pressure. Okay. So, why we say that is that if you ask what is the melting point of the liquid at this pressure, okay, at let us say P1, the melting point is equal to T1. Okay. At P2, the melting point is equal to T2. Okay. So, the slope of this line tells you how the melting point changes as you change the pressure. Okay. So, and this is given by, you can derive this relation called the Clausius-Clapeyron equation. You might have seen it in your thermodynamics classes. This tells you how this tells you the slope of this coexistence line, dt by dp. Okay, and you can derive that this is delta H. Delta H is the change in enthalpy of this transformation from solid to liquid, okay, divided by the melting temperature Tm times the change in volume of this transformation. Okay, and this transformation you can just write this as equal to delta H fusion. Okay, this is the enthalpy of fusion, okay, divided by Tm times now this delta V is the volume of liquid minus volume of solid. So, I will just write it as the molar volume of the liquid minus molar volume of the solid. Okay. So, this is exactly this equation. So, the molar volume of the liquid is usually more than that of the solid. Solid is more dense, okay, and you can see from here that in case the solid is less dense than the liquid, then this line will be sloped the other way. Okay, then the slope of this line will be negative. So, it will move in this direction. Okay. So, okay, and you can derive this relation very easily from this fundamental relation that the change in Gibbs free energy is V times dP minus S times dt, and okay, it should be have been a little imprecise. Okay, this P is same as the pressure. The C is same as the pressure. Okay, and if you divide this by the number of atoms or molecules, number of molecules, okay, then the molar, you get the molar Gibbs free energy, which is nothing but the chemical potential. So, the d mu can be written, and V divided by number of molecules gives you the molar volume dP, and S divided by number of molecules gives you the molar entropy times dt. Now, if you go from one point on the coexistence curve to another point on the coexistence curve, okay, then okay, now along the coexistence curve, the d mu of phase A should be equal to d mu of phase B. Okay, so A and B are two phases. So if you want to be more if you want to be in this particular case, so the d mu of the liquid should be equal to d mu of the solid. Okay, and so this implies that Vm of the liquid times dP minus Sm of the liquid times dt, okay, this should be equal to Vm of the solid times dP minus molar entropy of the solid times dt. Okay. And you can rearrange this equality, you can rearrange this equality, okay, to get the Clausius-Clapeyron equation. Okay. So, when you rearrange this, okay, you will first get dp by dt as delta s divided by delta v, okay, and then you can write the delta s as delta h fusion divided by Tm. So, we use we will first get delta s divided by delta v, okay, this, and delta refers to the transformation. Okay. So, you can easily derive this Clausius-Clapeyron equation, okay, and this is a very useful equation because it tells you the slope of the coexistence curve. Now, what you notice is that if you take a liquid and a solid, okay, so let me write it here. So, we will just write dp by dt is equal to, let me write this explicitly. So, let me write S liquid minus S solid, and this is the molar and I will put a bar just to indicate molar. So, the molar enthalpy molar entropy of liquid minus molar entropy of solid divided by the molar volume of the liquid minus molar volume of the solid. Okay. You can use for molar quantities, you can either use a bar or you can use an m. So, in this case I used an m subscript, here I am just using a bar. So, usually the liquid has a greater entropy than a solid, okay. So, the numerator is positive, okay, and usually the liquid has a greater molar volume than a solid. So, the denominator is also positive, and so the line, the coexistence line has a positive slope. Okay. Now, in rare cases like water, okay, the density of water is actually greater than that of ice. Ice floats on water. So, ice has a smaller molar volume. So, VL for ice is less than Vs, which is the molar molar volume of ice, is actually greater than that of water. Okay. So, ice occupies more volume than water, okay, and what that means is that this denominator becomes negative, and if the denominator becomes negative, then this whole quantity dp by dt becomes negative, and the coexistence lines has a negative slope. Okay. So, this is a very simple example of how you can understand lot of physical phenomena using this phase diagrams. Okay. Now, let us go to the last question. Okay. So, last question is a numerical question. So, we consider solid benzene, molecular weight 78 at 1 bar pressure, melting temperature is 278 K, the enthalpy of fusion is 9.9 kilojoule per mole. If the density of liquid benzene is 879 kilogram per meter cube and that of solid benzene is 1012 kilogram per meter cube at the melting point, okay, calculate the slope of the PT coexistence curve, and I should emphasize this is the slope at the melting point. Okay. So, again this is a straightforward use of the Clausius-Clapeyron equation. So, we can directly go to the solution. Okay. So we recall the, I will just write down the Clausius-Clapeyron equation, which says dp by dt is equal to delta H, delta heat of enthalpy of fusion times H divided by the melting temperature times delta V. Okay. So, delta H is already given. Okay. So, delta H was 9.9 kilojoule per mole. Okay. So, that is okay, and the melting temperature is also given. Melting temperature was 278 Kelvin. Okay. And all you need is to calculate this delta V. Okay. So, to calculate delta V, you need the molar volume of the liquid and the molar volume of the solid. So, the molar volume of the liquid, okay, you can calculate, okay, because you can take the molar mass, that is 78 divided by the density, that is divided by the density, that was given as 879 kilogram per meter cube. Okay, and this 10 raised to minus 3 is to convert grams to kilograms. So, the molar mass in grams is 78 into 10 raised to minus 3 in kilograms is 78 into 10 raised to minus 3 kilograms. You divide that by the density, okay, you will get the molar volume. Okay, so, the molar volume comes out to 8.87 into 10 raised to 5, 10 raised to minus 5 meter cube per mole. Similarly, the molar volume of solid benzene, okay, there all you have to do is to replace this 879 by 1012 and you get 7.71 into 10 raised to minus 5 meter cube per mole. And now, if you put this in the Clausius-Clapeyron equation, okay, then you will get an answer of 30 into 10 raised to minus 5 Pascal per Kelvin, 30 into 10 raised to plus 5, it should be 10 raised to plus 5 Pascal per Kelvin. Okay. Now, so you can calculate the slope of the coexistence curve. What is interesting is that if you want to change the melting point by 1 Kelvin, okay, then you have to change the pressure by 10 raised to 5 Pascal. Okay, and that is the reason why if you look at most phase diagrams, okay, the solid liquid coexistence line is very steep. It's actually very steep. Okay, so the slope of the solid liquid, this is a very steep line. Okay, because if you want to just change the melting temperature by a little bit, if you just want to change the melting temperature by a little bit, you have to change the pressure a lot. Okay. Incidentally, I should emphasize that if I write this equation backwards, if I write this equation upside down, okay, then I will get the if I write dt by dp is equal to Tm delta V by delta fusion H. Okay. This tells you how the melting temperature changes with pressure. Okay. And this is only, yeah, so this basically tells you how the melting temperature changes as you change the pressure. Okay. So, this gives you change of melting point with pressure. Okay. And now, in the case of water to ice, okay, you can see that as you increase the pressure, the melting point actually decreases. So, usually when you increase the pressure of a solid, it is harder to melt it, okay, but in the case of ice, if you increase the pressure, it is actually easier to melt it. Okay. So, in most solids, when you increase the pressure, okay, it is harder to melt, but in the case of ice, okay, when you increase the pressure, it is easier to melt, and this is something that you have seen in several experiments. Okay, you might have done in high school, or you might have played with a block of ice, and you might have seen that when you apply pressure, it melts, and when you release the pressure, it sometimes freezes back. Okay. So, I hope I have been able to give you some flavor of the basic principles and thermodynamics of solids. Okay, I have not put any questions from the topics like nucleation or the synthesis part. Okay, these are descriptive topics, and you will have some of those questions also in your assignment. Okay, in your first problem set. Okay, so with this I will conclude week 1 of this course. Thank you.